Weather conditions can have a dramatic impact on energy usage, especially within inclement climate zones. These impacts can make energy analysis difficult when trying to discern usage due to occupancy or equipment versus extremes in outside weather conditions. Weather normalization addresses this problem. Weather normalization is a calibrated adjustment to energy usage to remove the variability of weather. The process allows for an assessment of energy usage over time, regardless of the variable weather conditions year to year. Weather normalization begins with the gathering of actual energy usage and daily dry bulb temperatures from the nearest weather station. Weather stations are chosen automatically based on proximity, but they can be overridden in the weather normalization window. Actual usage is broken out into daily intervals and plotted against daily temperatures readings. Incremental regressions are performed from 40 degrees to 80 degrees Fahrenheit, establishing a mathematical correlation between actual energy usage and outside air temperature. Regressions are performed for each applicable energy source type in both heating and cooling environments. The regression with the strongest correlation is chosen as the weather signature. The weather signature identifies the balance point at which conditioning begins, the base load that stays constant regardless of weather conditions, and the slope that represents energy usage as a linear function to outside weather conditions. The balance point temperature is the temperature at which heating begins in the heating signature and cooling begins in the cooling signature. B3 does not assume a generic 65 degrees heating or cooling balance point temperature for all sites across an entire region. A unique balance point temperature is determined for each site for each energy source type. The balance point temperature is not a building's thermostat setting, though it is loosely related. Actual heating and cooling frequently lags thermostat settings due to factors such as insulation, daylighting, occupancy, etc. The Y-intercept baseload represents the energy usage that stays constant regardless of outside air conditions. For electric, these baseloads are typically plug loads, fans, and lighting. For heating energy source types, baseloads are typically hot water heaters and cooking loads. Average outside air temperature is utilized at the daily level to determine a weather normalization signature. Beyond that, B3 does not acknowledge average air temperatures at the monthly level due to temperature extremes that can occur within a given month. To better account for these fluctuations, B3 uses heating degree days and cooling degree days. Heating degree days is a calculation of the number of days and number of degrees below the heating balance point temperature that a site operates in each month. If a site's heating balance point is determined to be 60 degrees, all the days with an average daily temperature below 60 degrees are gathered and summated with the number of degrees below. Heating degree days can typically be 1,000 or more per month in colder climates during the winter months. Heating degree days are typically 0 during the summer months. Cooling degree days is a calculation of the number of days and number of degrees above the cooling balance point temperature that a site operates in each month. If a building's cooling balance point is determined to be 80 degrees, all the days with an average daily temperature above 80 degrees are gathered and summated with the number of degrees above. Cooling degree days can typically be 1,000 or more per month in warmer climates during the summer months. The slope is the linear relationship of energy usage as it pertains to heating degree days, cooling degree days. The bigger the slope, the more dramatic effect that weather plays on energy usage. If no heating or cooling pattern can be identified, it is considered a baseload-only signature. Weather normalization is not applied to baseload-only signatures. R-squared is a statistical measurement that represents the proportion of variance of a dependent variable that is explained by an independent variable. In short, it is a measurement of the closeness of theoretical usage as compared to actual usage. B3 displays this measurement as a percentage. A curve quality of 99% represents a high correlation of energy usage to outside weather conditions. A curve quality of 25% represents a low correlation between energy usage to outside weather conditions. It is not uncommon for delivery energy source types such as fuel oil and propane to be unable to determine quality weather signatures due to the nature of delivery and usage. Weather normalization is not applied to signatures with less than 50% curve quality. In addition to calculating actual HDD and actual CDD values for each month, B3 calculates an average HDD and an average CDD based on the last 20 years of daily temperature data. The average HDD and average CDD are crucial in applying weather normalization adjustments to actual usage data. The final step in the weather normalization process is applying the viable weather normalization signatures to actual usage to accommodate the differences in actual degree days compared to average degree days. That difference is applied to the non-baseload portion of usage. Contact B3 support for further details on weather normalization.